Okay, welcome to today's lecture on computational social choice. Today's lecture will be exclusively devoted to Arrow's impossibility theorem. So we will only talk about this theorem and in the end about some variants of this theorem. I showed you the statement last time at the end of the lecture. So there's no social choice function that satisfies IIA, Pareto optimality, non-dictatorship, and transitive rationalizability whenever there are at least three alternatives. So when there are only two alternatives, things are fine. So that would be, for instance, one way to get around this negative impossibility theorem, only choose from pairs. Then we can take majority rule, for instance, and all these axioms would be satisfied. So Arrow's impossibility is really a very impressive theorem. And Kenneth Arrow himself is also a very impressive economist. So he, as I mentioned earlier, he got the Nobel Prize for his work in part in social choice theory, but also in welfare economics. He's I think the youngest Nobel Prize laureate in economics ever. And what I personally find most impressive is that not only did he get the Nobel Prize, but 5 of his PhD students also got a Nobel Prize in economics. So in case you're wondering, that's Hassani, Meskin, Meyerson, Stieglitz, and Spence. So some of these names popped up in the algorithmic game theory course as well. Okay, so maybe one other thing, so to show you why we are putting so much effort into this impossibility, even though last time I showed you something that could be dubbed the poor man's version of Arrow's impossibility, because we are using a similar set of axioms for the Condorcet-May impossibility, and the proof was extremely simple, right? So we just showed there can be cycles in the majority relation. And the reason why we are spending much time on this as well is because the axioms, most of these axioms, are much, much weaker than what we have in the Condorcet-May impossibility. So for instance, if you think about anonymity and neutrality, so when I introduced them last time, I told you that these are really minimal conditions that should be satisfied by any fair social choice function. But clearly you can think of examples where anonymity is just barely violated. So we had these extreme examples like dictatorships where anonymity is completely violated, but you can think of examples, for instance, let's say you use plurality rule on any number of alternatives, you have 1 million voters, and the count of one voter counts twice. So here's double weight. Okay, so that would violate anonymity, so the impossibility doesn't apply. So the Condorcet-May impossibility doesn't apply because it's a function that is not anonymous. Similarly, you can think about just very minor violations of neutrality, for instance, where in certain cases where there's a tie between, let's say, two different alternatives, A and B, the choice will be made in favor of A, but only in very rare circumstances. And that's why the Arrow impossibility is so attractive, because it uses extremely weak conditions for the impossibility. Or in other words, so what Condorcet showed is like a specific failure of majority rule. There can be majority cycles, whereas Arrow's theorem is much more general. It doesn't only talk about the majority relation. In case you were wondering why there are 2 different years attached to the theorem here, so the theorem was proven as part of Kenneth Arrow's PhD thesis, and then he also published this as a book. And then 12 years later, somebody found an error in the first proof of the theorem. This person was called Blau, I think. And then this bug was rectified, and then there's a second publication or second edition of this book which fixes this bug. So it was only an error in the proof, so the statement is exactly the same. And that's why usually, or sometimes there are 2 years attached to that, because an error in the proof was fixed in an earlier version. Okay, so maybe some of you have seen Arrow's impossibility or heard about Arrow's impossibility in some other context. And that's exactly what we are doing today. So we are switching to a slightly different model where I think Arrow's impossibility is even more natural and more impressive. The reason why I phrased Arrow's impossibility the way I did is because in this course we are almost exclusively talking about social choice functions, because the application we have in mind is selecting alternatives. The original version of Arrow's impossibility talks about so-called social welfare functions, where the outcome of the function is not a set of alternatives, but it's a preference relation over the alternatives. Okay, and the nice thing is that these 2 statements of Arrow's impossibility are equivalent, but the version that you will see mostly in the literature is the one for social welfare functions, and that's the one that I'm going to show you now. So what's a social welfare function? A social welfare function is a function that maps a preference profile. Okay, so this is the domain of preference profiles, which we defined last week, So maybe to make this more precise, because we have fixed the domain of preference profiles to exactly this. So this is supposed to be a curly R. Okay, so the domain of preference profiles is just a preference relation for each of the voters. And this is mapped to a collective preference relation. So the purpose of a social welfare function is, so each of these individuals has a preference relation, and then we have some function which takes all these preference relations as an input and then computes a collective preference relation. So it's in some sense probably more natural than a social choice function, because you don't need this variable agenda which we had. You also don't need some kind of rationalizability condition, because the idea is just that the rationalizability is already contained in the social preference relation. Because if we are restricting attention to rationalizable relations, which we are doing in the social choice version of Arrow's impossibility theorem, we are basically making a statement about the rationalizing relation, because the social choice function that we are talking about has to be rationalizable. Okay? And rather than making this, this detour, we can directly talk about functions that map to a relation. And also intuitively, these functions are quite natural, because the question that Arrow was interested in was not really a question about voting rules, but it was like a maybe more philosophical or more general question of asking under which circumstances can we talk about the preference relation of an entire society of individuals. Okay, and in many applications, not only voting, this can be reasonable. So if you have a group of friends or the body of all the students, is there a reasonable definition of the preference relation of this entire group of people? And then he defined minimal axioms that such a preference relation should satisfy, and came up with this impossibility theorem. Okay, so in order to get this version of Arrow's impossibility for welfare functions, we need to redefine the conditions that are being used in the theorem. So as I said, so rationalizability basically just goes away, because we are now directly talking about a preference relation of the society of the agent. So this can be thought of as the rationalizing relation. And by definition, it has to be transitive, right? Because this set is the set of all complete and transitive relations. So that means we only need to redefine these three conditions here, which are just as natural as they are in the context of social choice functions. So let me show you something to make this clearer, so how these things are related. So by the way, so this is what I showed you last time, so how these two theorems are related to each other. But now I would like to show you how we get from a social choice function to a social welfare function, and why these two statements that I'm going to show you are equivalent to each other. So if we talk about the social choice function, we said, or we realized, especially in the lecture on choice theories, that once you require rationalizability, it all boils down on choices from pairs of alternatives, right? So if we talk about the social choice function f, and there's some preference profile, and the feasible set only consists of two alternatives, then we have a social choice function. No, that's not this. So f is the social choice function. Then if this function is rationalizable, as I said, so this can be rephrased by saying that we have this rationalizing relation, okay, which we are using this symbol for, and then in the subscript we have the choice function. Okay, and here the preference profile is fixed, and this dot here, so this is a notation I used last time already, so the dot means just it's a function of the agenda of the feasible set. So the preference profile remains fixed, and then this here in the subscript is just a choice function. For a fixed preference profile, it's just a choice function, so therefore this is the base relation here. Okay, so if x is chosen from the two-element set xy, then x is weakly preferred to y according to the base relation. And as I already said earlier, so now we are, rather than taking this detour, we are directly talking about functions that map a preference profile to a collective preference relation. So that means here we have x and y, okay, and the relation is just the output of the social welfare function. So it's g of r, and usually, so the collective preference relation according to some social welfare function will just be noted by this little symbol here without a subscript. So it's a preference relation for the entire society. Okay, so if this has a subscript, it's the preference relation of voter I or j or whatever. If there's no subscript, it's the collective preference relation according to some social welfare function g, for instance. And then this here is the rationalizing relation. And this here is a social welfare function. Okay, and the entire purpose of drawing this here is to show you that the concept of a social welfare function and a social choice function that is rationalizable, in particular transitively rationalizable, those two things are basically equivalent, because we can directly talk about a social welfare function that maps to a transitive relation by definition, and that is the rationalizing relation. Maybe one other thing that maybe is illuminating to some of you, once we talk about choices from pairs, we have three different possibilities. Okay, so if we have x and y, and the rationalizing relation or the, okay, I just realized this looks really ugly, so that's supposed to be SWF. So if we are choosing from x and y according to some preference relations, so these preference relations are always assumed to be reflexive. And then, for instance, it could be that x is strictly preferred to y, or it could be that y is strictly preferred to x. And the third possibility is that this person is indifferent between y and x. Okay, so these are the three cases we have here. In the first case, well, this element is chosen. In the second case, this element would be maximal. And in the final case, these two would be maximal. So this is just to show you that if we talk about choice from pairs, so we can either take the complete relation, for which there are three possibilities, so strict preference going either way or indifference, or there are three possible choice sets, taking only x, taking only y, or taking both alternatives. Okay, so as I said, so this is not a proof or anything, this is just an illustration to show you how social welfare functions oh, that was bad. Social choice functions and social welfare functions are related. In particular, if we talk about transitively rationalizable social choice functions. Okay, so now let's get back to the slide. So as I said, we need to redefine these three conditions here. And that's what we are doing now. So basically this notation is something that I already just explained on the slide. So if we have a social welfare function, then we will denote the collective preference relation by this, some call it curly greater or equal symbol, without a subscript. So then that's supposed to be the collective preference relation. It of course depends on what the function is. In almost all cases, this function will be called G to distinguish it from a social choice function, which will be denoted by F. Now the definition of these conditions, IIA. So if you recall, IIA I introduced as independence of infeasible alternatives. And there was a reason for that, because in the social choice context, it's about preferences over alternatives that are not in the feasible set, that are outside of the feasible set. If we talk about social welfare functions, there are no feasible sets anymore. We are basically just boiling down everything to pairs of alternatives. And therefore, what the definition of IIA becomes, we have two different preference profiles, R and R prime, and two different alternatives, X and Y. And then if the following condition is satisfied, is if the preference profiles coincide on the individual rankings of the alternatives X and Y. So that means the preference relations between X and Y are exactly the same in both of these preference profiles. Then the consequence should be that in the collective preference relation, that's this symbol here, for both of these different preference profiles, the collective ranking should also be the same. Okay? So intuitively, again, if you talk about a social welfare function where like all of us has a preference relation, it just says if you have two different preference profiles, and in both of these preference profiles, it's exactly this, the voters have exactly the same preferences over X and Y. So let's say I prefer X to Y and you prefer Y to X and you are indifferent and so on. It's exactly the same for both of these preference profiles. Then what we know about the collective preference relations in both of these profiles is that they should be identical, because the relative ranking of X and Y is exactly the same in both profiles. Or in other words, it should not depend on the ranking of unrelated alternatives or irrelevant alternatives, hence the name independence of irrelevant alternatives. So how X and Y are ranked collectively should be independent of how other alternatives different from X and Y are ranked by the voters. Okay, is that condition clear? Okay, Pareto optimality is completely straightforward. So the reason why I'm redefining it is because now we are talking about social welfare functions, not about a function that chooses alternatives, but here it's exactly what you would expect. If everybody prefers X to Y, then in the collective preference relation, X should also be preferred to Y. Okay? So that's like a weak notion of Pareto optimality. There are also other versions where, for instance, you say that if everybody only weakly prefers X to Y and some of them strictly, then the collective preference relation X should be strictly preferred to Y. But this condition is very weak, which makes the theorem even stronger. So it's good that it's weak. And I think this is also like if you think about social welfare functions, if you want to aggregate rankings of different individuals, it seems like really a minimal condition. Like if everybody agrees that X is better than Y, then collectively, of course, you should also have the same preference. The remaining condition is dictatorship. Dictatorship becomes the following condition for social welfare functions. So there has to exist some voter I or some agent I, such that for all preference profiles, and again, I emphasize the ordering of the quantifiers here. So first you fix the voter, and then you say for all preference profiles and all alternatives X and Y, if this person prefers X to Y strictly, then in the collective preference relation, X is also strictly preferred to Y, no matter what the preferences of all the other voters are. Okay, so that's a condition that should not be satisfied, right? So usually you talk about the function be non-dictatorial. But again, I think it's exactly what you would expect. So you have to take care, even sometimes I thought that even sometimes in books this is confused. So it's really important here that this is the strict preference and that's a strict preference as well. So because sometimes people think that dictatorship is something like a projection. So for mathematicians and hopefully also some computer scientists, you know that a projection is a function that would just map, it would be a social choice function where the collective preference relation would be completely identical to the preference relation of one of the voters. That's slightly different here because here we only say that if there's a strict preference for this dictator, then this also inherits to the collective preference relation. It doesn't say anything about weak preferences. Okay, so these are the conditions, and then the theorem is as follows. So every social welfare function that satisfies these two conditions, because rationalizability we don't need anymore because the collective preference relation has to be transitive by definition. So every social welfare function that satisfies the conditions has to be dictatorial whenever there are at least three alternatives. Okay, and I think in this form, if you weren't impressed by the version that I showed you before, I think here it's even more impressive because you don't need any fancy rationalizability conditions. You don't need to understand varying feasible sets. You only need this notion of a social welfare function, and then there are basically just two axioms. Because I rephrased it here, so you could also say there is no social welfare function that satisfies IIA, Pareto optimality, and non-dictatorship. Okay, but alternatively, we can just say, and I think this is a phrasing that makes it sound a little bit more appealing. Every function that satisfies these two desirable conditions has to be dictatorial. So dictatorships are because if it's phrased like this, you can think of it as a complete characterization of dictatorships, right? So dictatorships are examples of social welfare functions. So it's classes of social welfare functions where the strict preference of the dictator is inherited to the collective preference relation. And here we are showing that these are the only functions that satisfy IIA and Pareto optimality. And these conditions, as I said, seem really minimal. I'm going to show you an example to maybe even more convince you of IIA, but Pareto optimality, I think, is completely done, right? So nobody needs to be convinced that Pareto optimality is a reasonable condition. So again, to highlight why this is such an important theorem, so there's another very famous economist called Paul Samuelson, who advised several US presidents, and he said about this theorem that this is one of the most significant intellectual contributions of the 20th century. Because as you can imagine, it has not only applications in voting theory, but just for our general understanding of how to treat groups of agents. Because rather than only thinking about voting, you can just, as I mentioned earlier, think about the setting, which is the standard setting in welfare economics, where you want to argue whether there is a reasonable definition of a collective preference relation. And this theorem, well, it doesn't say there's no such condition, there's no such collective preference relation, but only very limited ones if we impose these minimal conditions. So in other words, these conditions are probably more demanding than they seem to be, in particular if they're taken in conjunction with each other. Okay. So, yeah, maybe now, unless there are any questions at this point. So this is the theorem that we're going to prove. So we are proving the version for social welfare functions, and these notes that are made in the other app are just to convince you that this basically also proves the same statement for social choice functions that we've seen earlier. But this version is just a bit nicer because we need one axiom less, and maybe it seems it's the more well-known version of the impossibility. Okay, so the one thing that I want to show you is, because sometimes people think, okay, Pareto optimality, that's clear, and of course we don't want to have dictatorships, that's also pretty obvious, but this IRA condition, okay, so I do understand the formal definition, but maybe it's a bit more demanding than it should be. People usually try to argue that maybe IRA is a condition that is just too strong. And well, I don't really want to convince you otherwise, but it's, I can show you some examples where it's obvious that a function that violates IRA clearly has some undesirable consequences. And the idea here is that if we just talk about like a typical application of a social welfare function, for instance, would be that we have, for instance, the entire body of students. That's the set of voters. And then we have a set of alternatives, which could be the courses that are being offered in computer science, for instance, at TUM. And then these students have preferences over these different courses, at least the ones that they have taken. So maybe it's undergrad studies or something, almost everybody takes the same courses, and then all the individual students have preference relations over the different courses. And then it would be nice if there's some reasonable function which can aggregate these preferences in order to get a collective ranking, which you, for instance, can publish in the student body newspaper or something to say that this is like the ranking of courses according to the students. And then also the conditions that we have here seem reasonable, right? So of course we want to have Pareto optimality. So if everybody thinks that, say, computational social choice is better than algorithmic game theory, that should also be the case in the collective preference ranking, right? And IRA is the example that I want to show you why it would be reasonable. And finally, of course, we don't want this function to be dictatorial, right? So we don't want to be, there shouldn't be a single student who can completely dictate the collective preference relation no matter what all the others say. And, oops, to give you this example, so that's a particular failure of one ranking function you could think of, and that would be a border ranking, but it works for any pointwise scheme. So if you have this application in mind, so one natural social welfare function, note that we are now talking about a social welfare function, not a social choice function, as we did previously when we studied Borders rule. You could just ask every student for their ranking of the courses. Let's just assume that the ranking is strict for simplicity, and then we can just let the students, or then according to this ranking, the students assign courses, like m minus 1 points for the first rank course, m minus 2 for the second ranked, and so on. Okay, and then we just add up all these scores, and then according to the sum of these scores, we get a ranking of the courses. So that is something that is actually done in many cases. It seems like that would output a reasonable ranking. But according to the theorem, well, this function has to violate one of the conditions. So clearly it's Pareto optimal. So if everybody prefers course X to course Y, then of course the score of X will be higher than the one of Y. It's not dictatorial, that's also obvious. So IRA has to be violated. And I will here show you an example which hopefully shows why such a violation is bothering. So let's assume, okay, so now it becomes a toy example again. So let's assume there are 5 students, but you can just add zeros if you like. It could be 500 or 5,000 or whatever. Just want to keep the numbers low. There are 3 students, for instance, or 300, if you prefer, who think computational social choice is their favorite course. So that's my wishful thinking. Then AGT, for instance, would be their second favorite course. And then there's some other course, let's call it course X, which they rank last. So here we only talk about 3 alternatives to show you this phenomenon that I would like to show you. Then there are 2 other students, or 200, which like AGT the best. And then they don't like computational social choice at all. I don't know why, but they do. And this course X is just in between there. Okay, now if we want to now compute the collective ranking according to this border function that I specified, the scores would be 2, 1, and 0 here. And then, for instance, if we count the score for AGT, that would be 3 plus 2 times 2, right? So 3 for the first column and 2 times 2. So the score for AGT would be 7. The score for computational social choice would be 6. Okay, right? It's just 2 times 3. And that means in the collective preference relation, which is just this symbol, AGT is strictly preferred to computational social choice. So it seems fair according to this preference profile. And then, of course, cos X is ranked last and gets a score of 2. So but the point that I would like to make is that AGT is collectively preferred to computational social choice. Okay. Now let's assume that this preference profile changes. Like, say, for instance, in the next semester. So 1 semester later, this professor who's teaching cos X for some reason screws up really badly. So cos X just becomes worse. Okay, so cos X is down here. It's just ranked last. So the only thing that changed is that this teacher who was teaching cos X just made a very bad course. The preferences between computational social choice and AGT remained the same among the students. So they didn't change. But if you now compute the scores, so now let's start with computational social choice. Well, then the score for computational social choice would be 8, right? It has increased by 1. The score of AGT would be 7. Okay, so it's still the same, but it's just worse than computational social choice now. Well, and cos X, of course, has now a score of 0. It's still last ranked. But the point that I would like to make here is that the preferences of the students between alternative X and CSC, they have changed, and this resulted in a change of the relative ranking of AGT and CSC. And that's a violation of IRA, because X is an irrelevant alternative. So it shouldn't matter how badly this other teacher screws up cos X. That shouldn't influence the relative ranking of CSC and AGT. And that is exactly what happened here. Okay, so that seems like this function, which is sometimes used, so it has at least this drawback of violating independence of irrelevant alternatives. Maybe another variant of this where things can go wrong would be the following here. Because here, so here in the example in this story with these different professors teaching courses, it's the other professor who did change something. So I'm teaching both of these courses, CSC and AGT, so I could also change the outcome without changing the relative ranking of CSC and AGT. And here the trick is just that course X remains as it is, but I now offer a new course in this semester. So I offer a variant of computational social choice, which is just a bit worse than the regular variant. Okay, so if you think about it, that shouldn't change the ranking of AGT and CSC. If I offer like a bad variant, let's call it computational social choice for dummies or something, so which is just like computational social choice, just a little bit worse. And that means, so here, that it's just ranked below CSC. Let's call it CSC prime. Maybe highlight it somehow. So this is this new course that I added, so it's just right below CSC. But the relative ranking of CSC and AGT didn't change, so students still think the same about those two courses. And now the same phenomenon occurs, so if I now compute the scores for CSC, then that would be 11. The relative score, or the border score for AGT is now, or is still 9 now. Oh, it is now 9. It was 7 before, but now it is 9. And of course, well, then these other courses can be ranked as well. So it's then CSC prime, and course X is still last ranked, 6 and 4. But again, the point is that here AGT was preferred to CSC. And now we were moving directly from here to here. I've only introduced a new variant of an existing course, and then suddenly CSC is better than AGT by this change in the preference profile. And that is not something that we would like to have. So both of these are examples So this phenomenon and this phenomenon, they're both examples of failures of independence of irrelevant alternatives. Okay, so that was meant to emphasize how important this condition is and why we want it to be satisfied. Is this clear? Okay, great. Okay, now here I need to go back. Yeah, okay, so I think I did praise the theorem enough to hopefully make you curious enough to actually want to see a proof of this theorem, right? And that's what we are doing now. If the clicker works. And before we get to the real proof, I do something that I mentioned in the beginning of the lecture. I'm going to show you a proof sketch just to show you how these different properties interact with each other. So basically, if you take away non-dictatorship, because the way I phrased the theorem, the consequence will be that only dictatorship satisfies these axioms, then there's only two different axioms. We only have Pareto optimality and IRA. And these two conditions have an interesting interplay, and that we will look at in a very special case of the theorem where we only have three different alternatives, so the minimum number of alternatives where the theorem holds. And only two voters, which is also the minimum number of voters for which the theorem holds. Okay, and if we have only two voters and three alternatives, then we can represent all the different preference profiles in a table like this. We made another simplifying assumption here. We assume that all the preferences are strict. Okay, so if there are only strict preferences, there are 6 possible rankings of these three alternatives for each of the voters, and that's why we have 6 rows and 6 columns, and that means 36 different preference profiles. So in general, of course, there can also be ties in the preferences, which would make this table larger. Just in case of maybe some of you might think that the theorem is just stronger if you prove it for strict preferences, but that's not the case. So the version for weak preferences and strict preferences are incomparable to each other. If you're interested, you can write a question in the forum and I can explain in detail why that's the case. But for now, let's just look at the simple variant for strict preferences, 2 voters, 3 alternatives, and see what's happening here. And just in order to save some space here, I just denoted preference relations as sequences of the alternatives. So this here means that the first voter prefers A to B to C. It's a strict preference relation. This here is the preference relation of the second voter. It could be BCA, for instance, and then in this cell here, that's the preference. So each cell corresponds to a preference profile, and the social welfare function returns a preference relation for both of these agents. And that means we are going to fill these boxes here with, again, sequences of 3 alternatives, which would be the collective preference relation. Okay, and we are using these 2 properties, Pareto optimality and IIA, and then in the end it will turn out that this table will exactly show a dictatorship, so a function which just copies the preferences of one of the voters. So, but the representation is clear, right? So I didn't use these greater symbols for preferences just to save space. And now the question is, how do we start? Okay, so we have Pareto optimality and IIA. Any ideas on for which kinds of preference profiles we already know what the collective preference relation should be? Okay, so maybe you first, because you raised your hand first. Yes, that's you. Okay, so the answer was, so we start with the diagonal because both voters have the same preferences. And we were using which axiom? Pareto optimality, right? So and I guess you had the same idea? Oh, okay. So if you start on the diagonal, both voters have exactly the same preferences, not only the preferences over one pair, but even over all pairs, the preferences are the same. And therefore, for instance, in this cell here, the collective preference relation needs to be ABC. Okay, so just by Pareto optimality. So if you now go to the next cell, which would be the one to the right, is there anything that we can do here? Of course, we could do the entire thing for the diagonal, as you said, but that's not how I prepared the animation. Exactly, A is preferred over B because both voters prefer A to B. And at the same time, A is also preferred to C because both voters prefer A to C. The first voter prefers A to C, the second one. But that doesn't completely specify the collective preference relation because we don't know how these two voters rank alternatives B and C. Okay, so that is left open here. And that is what is meant by this comma here. So we know A is preferred to B and we know A is preferred to C, but we don't know anything about the ranking of B and C. Maybe one more. So what about the next cell? What can I fill in there? Using Pareto optimality. Okay, A is preferred to C, that's right. And anything else? And B is preferred to C, exactly. Okay, so it seems like you all know what's happening here. So here, for instance, that is an example where only one pair is the same. Then it's B, C, and so on. Okay, and we can keep doing this for the entire table here. And then we have learned something about the collective preference relation. But of course, Pareto optimality alone doesn't do the job, so we need to do more. And now things are already a bit tricky because if you now think about IIA, IIA means if both of the voters have the same relative ranking of two alternatives, say A and B, then the collective ranking of these two alternatives should be exactly the same for all these profiles for which this is the case, but at that point IIA doesn't help at all. Therefore, what we are doing now is we are looking at one particular preference profile. Not sure I remember which one it was, I guess this one here. And then we make a case distinction. Okay, so the problem is we are now stuck, we don't know how to continue, but of course if we talk about the ranking of A, B, for instance, in this preference profile here, well, either A is preferred to B or B is preferred to A because we always assume strict preferences. And it could, we also allow for collective indifference, by the way. So we assume that individual preferences are strict, but the collective preference relation also allows for ties. Okay, that's just, I think, reasonable because, so for instance, if you don't rule out collective ties, then even majority rule doesn't fit in this framework. Because if you have two voters with differing preferences, but there is, of course, a majority tie. So therefore, we do allow for ties in the collective relation. So that means, for instance, for this preference profile here, there are three different possibilities. A is collectively preferred to B, or B to A, or there's collective indifference. And here, the first case is just, okay, it was this one, thankfully, that we just make the assumption that A is collectively preferred to B. Okay, so that is what is specified here. So the collective preference relation is A is preferred to B for this particular preference profile. So these are these two preference relations. Okay, and now that we have fixed this single profile, now we can use IIA quite a bit. Because what does IIA mean? So if the individual rankings of A and B are the same for two voters, so for instance here the first voter prefers A to B, the second one prefers B to A, and then we know that the collective preference relation prefers A to B, then this should always be the case whenever the first voter prefers A to B and the second one B to A. Okay, so if the first voter has AB and the second one BA, we know from this here, from this case assumption, that this has to be the case, for instance, also here. Because here the first voter prefers A to B, the second one B to A. Also here, first one AB, second one BA. Okay, so there are lots of consequences for other preference profiles because now we have fixed the relative ranking of A and B. Is that clear? So that's IIA. So all these orange or what yellow, I'm not sure what that color is. So all the cells that have this specific color here by IIA get the consequence that the ranking of A and B has to be exactly the same. Okay, so we always get AB here. Okay, now for this thing here, so let's again look at this particular profile where we made the case assumption. We can also deduce something from the definition of a social welfare function. It sounds a bit fancy, but it's really quite straightforward. So we know that collectively A is preferred to B and B is preferred to C. So the consequence would be, yes? Yes, A is preferred to C, and what I meant by the definition of a social welfare function is that a social welfare function maps to a transitive relation. Okay, so the collective preference relation has to be transitive, and therefore we know that A is also preferred to C. Okay, so by transitivity we have A, B, C here. Okay, and now we keep on doing this So now here, for instance, we have now fixed the ranking between A and C, or let's say the collective preference between A and C. So that means whenever the first voter prefers A to C and the second one prefers C to A, the collective relation will be AC. Okay, and that has consequences for many other examples as well. For instance, this one here. Okay, here also we have CA for the second voter and AC for the first one. So basically we are breaking ties in favor of the first voter, right? By this single assumption that we made in the beginning. So here then, for instance, also the collective relation will be AC. And similarly here, so we now know from transitivity that we have CB here. So that means whenever the first voter prefers C to B and the second one B to C, which is also the case here, for instance. Okay, it's BC and CB, then the collective relation will be CB. Okay, and now in the next step, we are doing this for all preference profiles. So this is always like the preference of the first voter, but the first voter prefers A to C, the second one C to A, or the first voter prefers C to B and the second one B to C. Okay, so what are we doing next? Okay, let me just take a peek. Okay, so what we do next is just, so these are just ordered tuples of pairs. There's a total of 6 of them. So I think now, since we did 2 more of these, we have now 5. So there's only 1 missing, and you can see that this table is being filled out more and more. So there are only a few cases for which this has not been decided yet. And now the missing case, I think, is IIA B, A. So that means where the first voter prefers B to A, and the second one prefers A to B. That would, for instance, be the case here. So first voter prefers B to A, second one A to B. So we know that the collective preference is BA. That means here it also has to be BA, right? First voter also prefers B to A. So that, for instance, resolves this, and it also resolves that. So the final step just resolves all the unsure boxes. So if that was too quick for you, you can verify it at home if you're interested, but you can trust me on that. And then the social welfare function is now completely specified. Okay, so it's exactly the function here, and the only properties that we used were Pareto optimality and IIA. Okay, so it's a complete characterization of this function. Note that we also made this case distinction, so we shouldn't forget about this. So at one point we just assumed the collective preference is AB, where there were 2 other cases left. But now regarding this case, so what can you tell me about this function? Yeah, it's a dictatorship, right? So it's just the preferences of the first voters are the collective preferences. So now I can finally use these fancy keynote animations. The first voter is a dictator here. Okay, and there were 2 missing cases. So there was one profile, I think it was this one here, where we assumed A is collectively preferred to B. So the 2 remaining cases are B is collectively preferred to A. If we do this, we can do a very similar analysis. It's almost analogous, and then voter 2 is a dictator. Okay, again, if you have too much time at your hands, you can do this at home, and then you will get a table where just all the columns are exactly the same. The other remaining case is social indifference here between A and B. So that would be this symbol here. And here it turns out that if you do this and use Pareto optimality and IIA a couple of times, then you get a contradiction. So this is not possible. So sometimes when we do case distinctions, it turns out that one of the cases is just not a possibility. But of course we need to prove it for that case because we don't know beforehand. So the only possible cases are that voter 1 is a dictator or voter 2 is a dictator. And that means the function is dictatorial, right? Because, well, the characterization by arrow, so it just left open who's the dictator. It just says if we satisfy these 2 properties, one of the voters has to be a dictator. It doesn't really matter which one because all dictatorships are undesirable. Okay, so I hope that this gave you some intuition on how these 2 different axioms work together in order to prove the theorem. And of course, well, that's not a complete proof now. Because we have only shown it for 2 voters, 3 alternatives, under the assumption that there are strict preferences and so on, but I think they already give you the basic idea. And of course, I dropped many things. So case 2 we didn't really look at, case 3 we also didn't look at, but it can be done like this. But the proof that I'm going to show you, like the real proof, which is based on Arrow's original proof, is much more intuitive. So here it's really just like filling out the table, and then in the end, miraculously, somehow we have a dictatorship, but it's It's not exactly clear how we got there. Okay, so before I show you the other proof of Arrow's impossibility, I would like to say something about computer-aided theorem proving, which is quite interesting because so this proof that I just showed you is from a political science textbook, so this table filling proof, just also to give intuition into the workings of these two axioms. And more recently, computer scientists have reproved Arrow's impossibility theorem using exactly the same approach. So the idea is just that they looked at the special case of three alternatives and 2 voters, and then what we did in this table filling thing was just done by a computer. Okay, so they just coded the axioms, and then they ask a computer to whether there exists a social welfare function that satisfies these axioms, and then the computer returned that there is no such function. And then, of course, what is missing to prove Arrow's theorem in full is that you need to extend this result to larger number of alternatives and larger number of voters. And this they did by manually proving an induction step. Okay, so there are 2 different dimensions here, so m and n. So m is the number of alternatives and n is the number of voters. So basically what they did, they proved that if there is a function that satisfies the axioms for any m and n, then there's also such a function for m minus 1 or n minus 1. Okay, and if you have such an induction step, then it remains to show the impossibility for only the smallest number of alternatives and voters, and that is what the computer did. Or if you want to phrase it the other way around, you can say it suffices to show that there's no such function for m equals 3 and n equals 2, because if there's no such function for this, according to the induction proof, which they did manually, so that means by thinking about this, there's also no such function for any larger m and n. Okay, so this was first done by Lin and Tang, and the reason why I'm telling you this is because the same approach has been used over and over again, in particular in my research group, in order to prove new impossibility theorems. So of course here, well, it was nice to see that a computer, that this is like a natural method of proving Arrow's impossibility using a computer, but it was already known that the theorem holds. But this becomes much more interesting if you want to prove statements which are not yet known. And this has been done in recent years using the same method here. So as I said, so they proved the so-called base case. That means 3 alternatives and 2 voters using a computer. And what they used is a set solver, which is a program that can decide whether a formula in propositional logic is satisfiable or not. So I'm pretty sure that some of you at least have heard about this. So who has heard about set solvers before? Okay, great. So sometimes in previous years there were mostly mathematicians in this course, and then this was one of the few things that they had never heard about. So the set problem, as also many of you will know, is NP-complete in general. So set solvers in the worst case may require exponential time, but in recent years there has been great improvements in set solving. And they work quite well for many practical instances of problems. And this instance here turned out to be very easy. So once you need to solve the base case only, or this induction start, this requires the computer less than a second. So it's very quick. Even though like something like brute force, if you were thinking about maybe why you need a set solver, you can just use brute force. Brute forcing doesn't work because the number of social welfare functions, even for these small parameters, is really large. Because what that means is you would need to look at the table, like the one that I showed you before, also include weak preferences, which makes the table a bit larger, and then just enumerate all possible fillings of this table, of course, and there are quite a lot of them, as you can imagine. So what we did when we filled the table, we used some like human intuition, and we used the definitions of the axioms. And basically that's also what the set solver was doing. So these axioms were encoded as part of this propositional formula, and for this example, that worked quite well. And then the set solver in the end said that this formula is unsatisfiable, which means there's an impossibility. And then adding the manual induction steps, they proved the complete impossibility. So what is a bit unsatisfying about this particular example of using computers to prove an impossibility theorem is that the induction step for varying m, so the number of alternatives, so that's very simple and easy because we have Pareto optimality. So this is something that we have done previously also in this course. We can just add new alternatives at the bottom of the preference relations, and they don't change anything. But the induction step for varying n number of voters, that's really tricky. And the induction step that they proved is is rather difficult, and it almost contains part of the proof of Arrow's proof already. So in this respect, it's not completely satisfying because the induction step required quite some work. But there are other examples. As I mentioned, we have been using the same technique in our group where the induction proofs for both M and N were extremely simple. And so then, for instance, in many cases, if you have weak preferences, the induction step for the number of voters just works by adding completely indifferent voters. So they usually also don't change anything about the preference profile, and that works for many other statements as well. And I think that's the last bullet here, which is something I told you already about. So in some cases in recent years, we were working on something, so we had a conjecture that maybe some axioms are not compatible with each other. We couldn't prove it manually, and then we at one point formulated it as a satisfiability problem, and in many cases we needed to optimize the propositional formula a lot in order to get a result, and in some cases we eventually found that the formula is unsatisfiable, and that gave us an impossibility result which was not known beforehand, and for which we didn't really have a human readable proof in some cases in the beginning, because we only had that the SAT solver says unsatisfiable. And then what we did for some of these statements, for the more important ones, we decoded a minimal unsatisfiable set of clauses. So now I'm getting maybe in too many details about SAT solving, but there's a minimal unsatisfiable set of clauses if something is unsatisfiable, and then we translated this back into a human readable proof. So in some of these cases we got proofs that we could publish in a paper which had like 10 pages or something, very ugly and nasty case distinctions, but they did the point and proved the theorem. So I think later in this course there's one other example where I will mention how SAT solving was used to prove an impossibility result in social choice. It turns out that in particular for social choice, this kind of approach is very useful and has been applied quite a bit. Okay. Yeah, I guess maybe now would be the perfect time for a break. Let's see, so maybe today's lecture will be a bit shorter than the other ones, but since we have really like a difficult proof to cover, that's fine. So what I'm doing after the break is show you like the real proof of Arrow's impossibility, not only this table filling thing. And then afterwards, I will show you a couple of variants of Arrow's impossibility, where people have tried to make one axiom stronger and another one weaker. We are not proving any of these, so there will be only one proof remaining in the lecture. But I prepared a nice animation where you can see that all of these other variants where you fiddled around with the axioms also led to negative results. Okay, so let's take a break until, yeah, I think 5:30 is fine. Okay. Okay, let's continue by proving Arrow's impossibility theorem. And in order to prove this theorem, we need a couple of auxiliary notions, namely the notion of a decisive group and of a semi-decisive group. So these concepts will be essential for the proof. Again, those of you who have printed out or in some form have in front of them the definitions that I upload before the lecture might want to use them. I'm going to define these notions here. So for this proof, we just fix some social welfare function g, and we assume that there are at least 3 alternatives. So these are the boundary conditions of the theorem. And then we define that a group of voters is decisive for A against B, where A and B are just alternatives, if the following is true. So if all of these voters strictly prefer A to B, then A will be collectively preferred to B. Okay, so that's the definition of a decisive group. So in particular, the preferences of all the voters who are not contained in group G don't matter. Okay, and this notion of decisiveness will be denoted by D subscript G, where G is just the group of voters. Okay, so I guess this definition is simple enough. So can you think of any example of a decisive group that we have already encountered? So I can think of at least 2 of them. Sorry? Dictatorship, yeah, that's a great example. So dictators are just singleton decisive groups. Right? So if you have a decisive group that only contains 1 voter, that would be a dictator. And how about Pareto optimality? So how is Pareto optimality connected to this notion of decisiveness? Exactly, right? So just a minor thing about terminology. So with Pareto optimality, so Pareto rule is a specific social choice function that we have defined. But if we have Pareto optimality, as we do have here, because that's one of the conditions for error, we know that the entire group of voters N is a decisive group. Okay, so that's two interesting examples of decisive groups. So, okay, so this is something I didn't really define yet. So decisiveness is defined for certain pairs. So we can say that a group is decisive for A against B. And if this is the case for all pairs of alternatives A and B, then we say that the group is decisive. Okay, but that's what we already did when we talked about dictatorships or the entire group of voters being decisive if the function is Pareto optimal. Okay, so if G is a dictatorial function with dictator I, then there's this singleton decisive group. If, for instance, maybe here we can draw a little figure. If we have majority rule, for instance, and now again, let's emphasize that for majority rule, it's only defined for two alternatives, which I said at the beginning of the course. But if we have only two alternatives, and let's say 3 voters, for instance, let's say these 3 dots here are the 3 voters, then the decisive groups, if we have majority rule, would be this here, because it's a majority, right? That here, because it's another majority. This is also a majority. Well, and of course, the group of all voters would be a decisive group. Just to give you an example of the notion of decisiveness somehow represents the power structure for a given social welfare function. For majority rule, for instance, it would look like this. And then, as mentioned before, so if G is a Pareto optimal function, well, then, of course, the entire group of voters would be decisive. Okay. Now there's one other notion, and that's the condition of so-called semi-decisiveness. So I don't really like this term because semi usually sounds like it's like half decisive or something, but it's really just a weak form of decisiveness. So you can think of this as weak decisiveness, and the group is weakly decisive or semi-decisive for A against B, denoted by the same symbol, only with a little tilde on top. So there's this curly wave on top of the D here. If it holds that if all voters in G strictly prefer A to B, and all the remaining voters strictly prefer B to A, then in the collective preference relation, A should be strictly preferred to B. Okay? So it's like a special case of the previous definition, where we also fix the preference relations of the other voters not contained in G. So for decisiveness, it doesn't matter what the preferences of everybody else is. Here we say that for a specific preference profile, where all the voters' preferences are fixed, everybody in G strictly prefers A to B, everybody who is not in G strictly prefers B to A. If this group G is semi-decisive, then the collective preference relation should be A strictly preferred to B. So it may seem a bit arbitrary why we define it that way, but this is just a tool that we need in the proof. And also realize at this point already that a group being like semi-decisive is not something that is really unusual. So for instance, if we completely rule out collective indifference, so which we don't in general, but if for the sake of the example, if we rule out that there's collective indifference, then any group G or its complement has to be semi-decisive. Right? Because if you look at the preference profile where everybody in G prefers A to B and everybody not in G prefers B to A, well then if there's no collective indifference, then the social outcome should be A is better than B or B is better than A, and depending on what it is, one of these two groups is semi-decisive. Right? Okay. Also, like a comment about decisive sets, like the first definition. So decisive sets, so I drew this example for majority rule where we had these overlapping decisive sets. So is it possible that you define a social welfare function where there are two decisive sets that are disjoint? In the example that I drew there, that was not the case, but can you think of an example where there are two disjoint decisive sets? Give you some time to think about that. No ideas? Well, you cannot think of such an example because no such example exists, right? So it's impossible that two decisive sets are disjoint from each other. Why is that the case? Well, if everybody in the first set, if it is a decisive set, prefers A to B strictly, then the collective preference relation will be A is better than B. If there's another decisive set, which for the very same pair is also decisive, so they can force the collective preference relation to be B is strictly preferred to A by aligning their preferences accordingly, but that's not possible. Right? It's like having two dictators. I think that's also something that we cleared out early, so it's impossible that there are two dictators. Because if they have different preferences, well, then they cannot be a dictator. They cannot be a dictator. Is that clear? Okay, so the decisive group has complete power over the collective preference over two alternatives, and it's impossible that two disjoint sets have complete power. Okay, so far these are just definitions, but these will be essential for proving the theorem. And obviously, so if for some pair of alternatives we have that a group G is decisive for A against B, then it is also semi-decisive, right? So the notion of decisiveness is stronger because, well, decisive means no matter what the preferences of everybody else, whereas semi-decisive means even if the preferences of all the other voters are exactly the opposite of the ones that we have in G. Okay. Now I try to boil down, or not boil down, it's really a complete proof. So I try to condense the proof of Arrow's theorem into just 2 slides. So usually the proof is split into 2 different lemmas. So this is the essence of the proof. So this is usually called the field expansion lemma. And then the remaining part is sometimes called the group contraction lemma, but I didn't call it lemma here. So I need some more space on the slide. That's why there's no heading here, but I try to put everything on the same slide. So if you understand the proof of this lemma here, then you really have understood the essence of Arrow's impossibility. Okay, so what does the lemma say? So it says that if we have a social welfare function G, and it satisfies IRA and Pareto optimality, so these are the conditions of Arrow's impossibility, and if we have some group G, okay, if the following holds, so this is an implication, so if this here holds, then this is also true. So this here means there is some pair of alternatives, 2 different alternatives, such that this group G is semi-decisive for A against B. Okay, so if G happens to be semi-decisive for some pair, then the consequence is that the same group G is decisive, not only semi-decisive, for all pairs X and Y. Okay, so the implication from here to here contains 2 strengthenings. The first one is we are going from semi-decisiveness, there's no tilde up here, to decisiveness, and we say if some group is semi-decisive for one pair, then it's also decisive for all the pairs. So that's the second strengthening, so all pairs. So we are going from one pair to all pairs, and we are going from semi-decisiveness to decisiveness. Okay, so what this means is that under the axioms that we have in Arrow's impossibility, semi-decisiveness implies decisiveness, and even more, because we can only assume it for one pair, and then we do get it for every pair of alternatives. And in order to show this, we need to show 2 intermediate steps. So first, of course, we assume that there are these 2 alternatives, A and B, and this group is semi-decisive for A against B. So these are just the conditions taken from up here. And then we want to show 2 different consequences. So let me somehow, I don't know, let's take blue here, underline these. So these are the 2 statements that we want to show. And then in the end, I will show why these are sufficient to get decisiveness over all pairs. So we show that if G is semi-decisive for A against B, then it is also decisive for A against X. X is just some other alternative, and also decisive for B against X. Okay, so essentially what we are doing here is just that we are taking a single semi-decisiveness relation, and we are deducing that there are 2 other ones, and not only semi-decisiveness, but even decisiveness. Okay, and we will now show the first statement here. Okay, so this corresponds to this. We only want to show that G is decisive for A against X. And the only properties we can use are, again, IRA and Pareto optimality. So you can like recall the proof sketch that I showed you where we filled out this table, because that also showed the interplay between PO and IRA. So in order to show the statement, we take an arbitrary preference profile over which the following is known. All the voters in G have the preference relation A, B, X. So we only need the preferences over those three alternatives. Okay? So they prefer A to B and then X. All the other voters who are not in the group G, we don't know their preferences. The only thing that we know is that these voters prefer B to A and B to X. But in particular, we leave completely open the relative ranking of A and X. So if we only look at the preference profile restricted to these three alternatives, it means that the other voters think B is the best out of these three alternatives, whereas for the ones in G, the preference relation is completely specified. So if you want to draw a preference profile like this, it's an incomplete preference profile. It could look like this. Okay, so the first voters in group G have these preferences here. The other ones prefer B the most, and then AX could be anything. Could be A is better than X is better than A. There could be indifference. Anything would be allowed here below. Okay, and now what we are doing, so we are now like deducing some statements about this particular preference profile. So we know, and this is the assumption that we are starting with, that G is semi-decisive for A against B. Okay, so that means if everybody in G prefers A to B, and everybody who's not in this group G prefers B to A, and that's the case, because B is definitely on top of A. Okay? Well, then in the collective preference relation, A is preferred to B. Okay, so that's just really using our assumption that G is semi-decisive for A against B. So in the collective relation, A is preferred to B. One other thing we also know from this preference profile here is that there is a Pareto optimality, or a Pareto dominance. So B is preferred to X by the voters in group G, and also everybody in here prefers B to X because B is just on top of both A and X. We don't know how A and X are ranked, but B is on top. So everybody prefers B to X, so by Pareto optimality, B is also collectively preferred to X. Okay? So I really like this proof because the individual steps are so simple, and then in the end, I guess like two steps from now you will be a bit surprised because we're almost done with the first step already. Okay, so we have that A is collectively preferred to B and B is collectively preferred to X. Now, one other condition that we have, which is implicit in the definition of a social welfare function, is that the collective preference relation is transitive. Okay, and this is also something we used in this table proof. If A is better than B and B is better than X, then by transitivity, A is also better than X. Okay, and now I said we are almost done with the first part, because what do we want to show here? So we want to show that G is decisive for A against X. Okay, that means if everybody in G prefers A to X, and we don't know anything about the preferences of the voters who are not in G, about their preferences between A and X, only these two alternatives, then A should be collectively preferred to X. Now here we do have a class of preference profiles. The only assumption we made that everybody in G prefers A to X. Everybody who's not in G, we don't know their preferences between A and X. It could be anything. Right? It could be that they are indifferent, some of them, maybe some of them have strict preferences, we don't know. But we do know that the social outcome will definitely be A is preferred to X. And since we have IRA, so now it's really that's really the tricky part in the proof. Since we have IRA, we know that this extra alternative B that we have here, so which we sort of introduced, it can't matter, it can never matter. So it doesn't really play a role here. So that means in any preference profile where A is preferred to X by the voters who are in group G, and the other ones have any preferences over A and X, A must be collectively preferred to X. Okay, because we have found one class of preference profiles here where we have this extra alternative B here, which cannot matter, and by using Pareto optimality and transitivity, we have deduced that in the collective preference relation, A is to be preferred to X. Or maybe slightly more formally, so by independence of relevant alternatives, we have that in any profile R prime in which all the voters in G prefer A to X, A has to be collectively preferred to X. Because the only thing that we know about this class of profiles here in terms of the ranking of A and X is that everybody in G prefers A to X and everybody who's not in G doesn't. anything else, like how B is ranked, doesn't matter. And that already shows that this group G is decisive for A against X. Because if this is the case, so for any profile here for which this is the case, the social relation has to be like this. That's exactly the definition of a decisive group. So G is decisive for A against X. Okay, so what usually puzzles people at the first time is how we can draw a specific preference profile here and then draw such a general conclusion, but it is because of IRA. Okay, so you can also think of it the other way around, where we just take an arbitrary preference profile where A is on top of X, and we don't know anything about the relative ranking of A and X by the other voters, and then we construct this preference profile here from scratch, which has the same, where the voters have the same preferences over A and X if they are contained in the group G, and there's this new alternative added. Then we get this consequence that A has to be preferred to X, and then we can just remove B from consideration again and look at the original preference profile, because only the ranking of these two alternatives matter. Okay, are there questions at this point? So what I now claim is that we have shown the first part here, and the second part is somewhat similar, slightly different. It's not exactly the same, but once we have shown both of these, we are almost there at having shown this statement here. Yes? Why we assumed it in this preference profile here? Okay, so because what we want to show in the end is that we want to show that group G is decisive for A against X. So we need to have some preference profile where everybody in G prefers A to X. Okay, otherwise we can never get such a consequence like this one here. So we need to have some preference profile where A is on top of X. And that's why we picked it that way. So in principle, we could have picked any preference profile, but this is just, so of course, if when Arrow proved this statement for the first time, probably he was thinking about many different options here on how to proceed, but it turned out that this particular construction here gives you the statement that you need in the end. Okay, so I guess let me show you the second part, and because it is using similar kinds of arguments, maybe it makes things a bit clearer. Okay, for the second statement, well, actually, I think I can. So this is always a bit ugly directly on the slide, but let me show you what we are basically showing here. So we have these two alternatives, A, B. Then this arrow is depicting the decisiveness relation. So this is like weak decisiveness. So we are assuming that this group G, let's just drop the subscript G here because I don't have much space there, that this group G is weakly semi-decisive for A against B. And then the consequence, what we are showing here is, maybe let's use a red color for this, is that we have like a real decisiveness, not only semi-decisiveness from A to X. That is what we have just shown. And then in the second step, we are showing that we also have that this group G is decisive for A against X. Okay, so this is the second step. So this is also decisiveness, and okay, let's see. This is 1 and this is 2. Okay, so these are the two steps of the lemma. Okay, so now for the second part, we again take in preference profile. We somehow magically arrange these three alternatives in order to get what we want in the end. So all the voters in G prefer B to A to X, and everybody else, we only know this about them. So we know that these voters prefer B to A and X to A, but we don't know the individual rankings between B and X. Or in other words, out of these three alternatives, A is ranked lowest. Okay, so it's a bit similar to this one here, only that we know is that A is ranked lowest, and we don't know the individual ranking of B and X. And here you can already see why we are completely leaving open how B and X are ranked, because in the end, we want to have this consequence here, which means that the preferences of all the voters in G between B and X are fixed, and the ones who are not contained in the set G, we don't know anything about their preferences. That's why it's being left open here. So if we draw this preference profile, you could think of it like this here, where the BX preferences are left open. Okay, so what we do now is that we first use the statement that we have just shown above. Okay, so we know that that G is semi-decisive for A against B. So this is our assumption that we are making throughout this proof. Therefore, what we have just shown is that G is decisive for A against X. Okay, also in this preference profile, G should be decisive for A against X. Okay, here the voters in G prefer A to X. It doesn't matter how they rank, how the other voters rank X and A. If everybody in G prefers A to X, well, then in the collective preference relation, A has to be preferred to X. Okay, so by what we have shown in 1, we have this here. So collectively, A is preferred to X. Okay, reusing what we proved up there. Now, again, we also have Pareto dominance in this profile here. Everybody prefers B to A. So for the ones in G, this is obvious. For the other ones here, well, one of the few things we know is that they all prefer B to A. So everybody prefers B to A, so collectively B is preferred to A. And now the rest is almost exactly the same as before. So we know that the collective relation is BA and AX. And just like here, we can use transitivity. And that gives us B is preferred to X. Okay, and now we are using the same kind of argument here. So it's in case you have maybe, I don't know, maybe something like doubt about this proof. So this is really the step that most people struggle with. And we are doing exactly the same once more. Because here again, we are arguing that we now have a preference profile here where everybody in G prefers B to X. We don't know anything about the ranking of the two alternatives B and X by the remaining voters, but we do know that the collective preference relation has to be B is preferred to X. So that means in all other preference profiles where B and X are ranked just like in here, the collective ranking has to be the same. That's IRA. So any profile in which B is over X for the voters in G, the collective relation has to be B over X. So by IRA again, crucial step, we have that for all profiles in which everybody in G prefers B to X, B is also collectively preferred to X. And this is exactly the definition of G being decisive for B against X. So whenever those guys here prefer B to X, in the collective relation, also it has to be preferred to X. That proves the second statement here. Okay, so we have if G is semi-decisive for A against B, we also have that the same group is decisive for A against X and decisive for B against X. Okay, yes. No. Okay. So the question of whether a group is decisive. Okay. So you mean in the second step? So this is particular in the second step. Okay. Yeah. That's a good point. So, but whether a group is decisive or semi-decisive doesn't depend on the preference profile. So if a group is decisive or semi-decisive, that's a property that holds for all preference profiles. So it's not a property of a single profile. Yeah, but here we showed that if A is semi-decisive for A against B, okay, then in general for all profiles, G also has to be decisive for A against X, but not only in this particular profile, in any profile. In particular for decisiveness. So decisiveness is not a property, so maybe you can think that semi-decisiveness is a property of a single profile, because well, in the definition, we specify the preferences of voters in G and all the voters who are not in G completely, right? So here you can think that this is really just a property of a single profile. But what we showed in the first statement here is that if this here is true, then we have this consequence here, which is real decisiveness, and that's clearly not a property of a single profile. So this is a consequence for all profiles in which A is preferred to X by the voters in G, but all the other voters can have any preference. Okay, so I guess it's part of the magic of IIA what you are struggling with. So, yes? that's exactly what we're doing in the remaining 2 bullets, whether this relation is symmetric. So by definition, it's not clear whether it is symmetric, but the statements that we have shown, we are going to see that this relation is complete and symmetric under these conditions here. So in general, it doesn't have to be, but it follows from what we have shown that this decisiveness relation is complete and symmetric, and that means that between any pair of alternatives, so if some group, this is what we want to show in the theorem, so this actually brings us exactly to what we want to show in the end. We want to show that for any pair of alternatives, the same group is decisive for x against y. And by having shown these 2 statements here, it follows quite straightforwardly that this has to be the case. So this relation dg here is symmetric, and it is complete. Okay, so maybe since we talked about this already, so let me show you this, or maybe before answer another question. Yes? Okay, so it's just defined like on the previous slide. I don't want to go back because otherwise I lose my drawings here. So, but the definition says, so for instance, you're asking about semi-decisiveness or decisiveness? Okay, for semi-decisiveness, the definition is if everybody in the group G has A on top of B, and everybody who's not in this group has B on top of A. Okay, so then for this preference profile, there's a certain consequence. But the definition of decisiveness works for an entire class of preference profiles. But I think you were asking what this for and against means, right? So for A against B means that you have A on top of B if you're in group G. Was there another question here? Okay. So then let's see what we can now say about this decisiveness relation, because we were already asking about symmetry and also completeness. So we have now shown that if we have this relationship between A and B, then as a consequence we have this stronger relationship, denoted by the red arrows, between A and X and B and X. And now if we only take, let's only focus on the second one here. If we only take the second one here, then it's already obvious that this relation has to be complete, right? So now let's say we have an arbitrary number of alternatives. I don't know, maybe like this, and then we start, let's say the first ones are A and B, so we start with this semi-decisiveness between A and B, or for A against B. Then by using this red thing repeatedly, so since decisiveness is stronger than semi-decisiveness, we can, once we have added this arrow here, because this is what we get, right? If we assume this one is there, and then we can draw this red arrow here, so we can like form a path using these edges here. Any red arrow is also a black arrow, right? Because decisiveness is even stronger than semi-decisiveness. So that means we can repeatedly use the second condition, and then we, I don't know, can do something like this. We can go to this here. We can just walk around here. And for instance, form a cycle, and then we would have shown that this relation is complete. So between any pair of alternatives, there has to hold a decisiveness relation. And we can even do something more, since we have 5 alternatives here, we can go back up here, then we can go in this direction, then we can go down here, then we can go down there, and then maybe up here. So I'm not drawing everything here, but I think it's obvious that if we only use the second condition, this condition here, we can completely fill this graph with arrows, which means that the relation is a complete symmetric relation. Okay? By just walking around and using only the second condition. This only works if we have at least 4 alternatives. For the case of 3 alternatives, we also need this first condition here, which we haven't used yet. And the reason is, so here for these 5 alternatives, for instance, I think it's pretty straightforward, so we can just walk around, and then since there are more than 3 alternatives, there's enough space to just turn around if we are walking around in this graph, and go around in this graph in the other direction. If we have only 3 alternatives, like in this example here, we would start with one black arrow, which is the semi-decisiveness relation between A and B. Okay, if we only use the second condition, we have this here, then we use the second condition again, we have this here, well, and then we do get completeness, but we don't get symmetry. Okay, so we cannot go, we don't have enough space for maneuvering and turn around in this small graph here. But this we do get if we have the first, if we also take into account the first condition here, because if you, maybe let's, so this is A, this is B, this is X, this is only what we get from the second condition. If we now also use the first one here, we have also G is decisive for A against X. That means we get an arrow from here to here. Okay, and once we have that, we go like this, like that, and like this, and then we have also shown that this relation is complete. So sometimes in some textbooks you will see that people don't want to confuse the readers by having this extra argument here, and then they just show Arrow's impossibility for at least 4 alternatives. But since we have shown 1 anyway, and we need 1 for proving 2, I decided to show you the full proof. So let me reveal these final bullets here. So repeated application of 2 implies that the relation is complete. So this is what we did here. Okay, so here we even had enough alternatives to also show that it's symmetric, but if we only use 2, we only get completeness. That means between any pair of alternatives x and y, a decisiveness relation has to go in one direction or the other. And if we also use 1, we get that dg is symmetric. Okay, and the proof for this is, and this only works for at least 3 alternatives, and the proof is exactly what we have here, which is just this figure here. Okay, so we need to use the second statement and then the first statement, and then we get that if G is decisive for X against Y, then as a consequence G is also decisive for Y against X, and this shows symmetry. So if you think about these graphs, so we are basically showing if you have a graph and there's one black edge in there, so if some group of voters is semi-decisive for one alternative against another, we don't know which ones, just one pair, and one group like this exists, well, then we can fill the entire graph with red edges going in both directions. And this is exactly what this statement here is about. So this is the single edge between A and B, and then the consequence is that we have red edges between all pairs of alternatives. And that makes the consequence so strong, right? So we have a single semi-decisiveness notion, and then we get decisiveness between all pairs of alternatives as a consequence. Okay, so if you still have questions in your mind and you're not absolutely sure how this is working, so don't worry about this. So it's everybody who sees this proof for the first time has some trouble, and this theorem is so deep that even after many years of teaching it, so when I'm reading about it, sometimes I discover new angles and new aspects of it, even after years of having studied it. So it's this is one of the examples where probably looking at things at home again is worthwhile, because then you might get a deeper understanding of what's going on. But this only proves the lemma, so I would now like to continue and prove the rest of the theorem. But this, as I said, is really the heart of the proof, so the rest is really relatively easy. Okay. Yeah, there was one thing that I wanted to mention, which I didn't mention yet. Because that is useful for the homework exercise. If you notice carefully, so we have used Pareto optimality, we have used IIA, and we have used transitivity at one point, or at 2 points. So here we use transitivity in the very same way, but notice that quasi-transitivity is already sufficient here. Right? Because we have strict preference, consequence is a strict preference, and quasi-transitivity is a weaker notion of transitivity. And the same is true here. So that means this part of Arrow's impossibility would also work if the social welfare function only has to return quasi-transitive relations rather than transitive ones. That's not true for the rest of the proof, but this part can be reused because there are variants of Arrow's theorem where the collective preference relation only has to be quasi-transitive or maybe even acyclic. Okay, so that's just a comment on this proof. Okay, but now what we have established, I think that's also on the slide, okay, is that if some group is semi-decisive for some pair, then it is decisive over every pair. Okay, and we are going to use this in the remainder of the proof, which is sometimes called the group contraction lemma or splitting lemma. And the reason here is we start now. So we have, as I said, so the decisiveness notion defines the power structure within a set of voters according to a certain social welfare function. And now we have a consequence using decisiveness. And the only thing that we basically know about decisive groups in general, about social welfare functions, that satisfy Arrow's conditions is that the set of all voters has to be decisive, okay? Because we have Pareto optimality. So that is something that we said a couple of minutes ago. So the group of all voters has to be decisive. But that is still far from dictatorship, right? So the group of all voters has to be decisive. What we want to have in the end is that a single voter has to be decisive. And that's why it's called the splitting lemma, because what we are showing is that if some group of voters is decisive, then we can partition it into two subgroups such that one of them is decisive. And both of them are non-empty. So we can partition it into two non-empty groups of voters such that one of them is decisive. Okay, does anybody see why that would yield the proof in the end? Okay, so why this lemma is, yes? Exactly, yeah, because you keep partitioning, so you start with a group of all voters, then you divide it into two, and one of these groups, by the proof that I'm going to show you, has to be decisive. You keep on doing this, and this is implicitly where it is used that there's a finite number of voters. And this is important, it's an important assumption in Arrow's theorem. So there are some extensions to infinite numbers of voters, but then you need to make extra assumptions. So here you really need finiteness, because you keep on splitting the set, and you always get smaller and smaller decisive groups until in the end you have the smallest decisive group, which would be a single voter. Because these always have to be non-empty. It's not the empty set that is the smallest one, but it's a singleton set. Okay, so that's the idea for the rest of the proof. So we let G be a decisive group which contains at least two voters. Okay, so and this is also an assumption that is implicit in Arrow's theorem. There are at least two voters and at least three alternatives. Now we know that such a set must exist because of Pareto optimality. Okay, so there's the set of all voters clearly is decisive. Then we partition this group into two non-empty subgroups, G1 and G2. Okay, so here we have, this is really what defines a partition. So these are, the union of it is G, and they are disjoint. And then we consider a certain preference profile. Okay, again, we are using one specific preference profile to get the contradiction in the end. Or maybe not a contradiction, because in the end we get the result that there has to be a dictator. And what's really nice about this here, that's why I'm saying familiar preference profile, or maybe, yeah, so who remembers this kind of preference profile? So does it ring any bells? Have you seen that one before? Yes? Yes, the Condorcet paradox, right? So it's the example where we had the cyclic majority relation. And as I mentioned at the beginning of today's lecture, so Arrow's theorem is so impressive because it's not just a statement about the majority relation, but the essence of Arrow's proof is again a preference profile which looks very much like the Condorcet cycle profile. So it's not exactly the same because we don't have exactly three voters here. So everybody in G1 has these preferences, everybody in G2 has these preferences, and all the remaining voters have those preferences here. This could be empty, right? So this is, we only say that these two sets are non-empty. In principle, this could be the empty set. Okay, and now we are again like doing some magic tricks with IIA and Pareto optimality. So the only thing that we know about this group G is that this group is decisive for any pair of alternatives. And since this group G is also decisive for B against C, note that everybody in G, so G are these two columns taken together, so both of these columns here, they prefer B to C. We know that collectively B has to be preferred to C. Okay, so that's the definition of decisiveness, and we know that G is decisive by assumption. So G is a decisive group. So B has to be collectively preferred to C. Now we distinguish two different cases. And those concern the collective preference relation. So it's maybe a little bit like what we did in this table filling proof where we also had this case distinction. In the first case, A is collectively preferred to C. So in principle, there are three different possibilities for the collective preference between A and C. A is preferred to C is preferred to A, or there's social indifference. In the first case, A is collectively preferred to C. Now, we know that in G1, everybody in this group G1 prefers A to C. Okay? And everybody else prefers C to A. And Since in the collective preference relation, by assumption, A is preferred to C, well, then this group G1 is semi-decisive for A against C, because in this particular preference profile, everybody in G1 prefers A to C, and everybody else prefers C to A. And in this preference profile, A is collectively preferred to C, and that means that this always has to be the case, no matter what all the other alternatives are ordered. And that means we have shown that this group G1 is semi-decisive, so this weaker notion of decisiveness, for one particular pair, AC. But the lemma has shown if some group is semi-decisive for some pair, it is decisive for all pairs. Okay, and that means that G1 is decisive. So we assumed that this group G, which consists of these two columns here, if it is decisive, then in the first case, this group is decisive. So we have found a smaller group which is decisive, which is the goal of this proof. We want to find a smaller group which is also decisive. Now the remaining case, so here we only need two different cases because we can, so as I said, so then in principle there are three different ones, but two of them are captured by this one here, social indifference and C being strictly preferred to A. So if C is weakly preferred to A, and we know that B is strictly preferred to C, then we know by transitivity that B is strictly preferred to A. Okay, so B strictly to C, C weakly to A. Here we really need transitivity, not only quasi-transitivity. So we have a strict preference from B to C, a weak one from C to A. Well then, as a consequence of transitivity, B has to be strictly preferred to A. So you could prove this individually. So if you have it's like a special application of transitivity where one of these arrows is strict and the other one is weak, then in the consequence you also have to have a strict arrow. But since we are talking about full transitivity here, you can just read these symbols just like greater or equal symbols for natural numbers, for instance. And if B would be a natural number strictly greater than C, and C is at least as great as A, then of course B would be strictly greater than A as well. Right? So this just follows from transitivity. Okay, so that means we have that B is collectively preferred to A. And now again, by IIA, if we look at the group G2, everybody here prefers B to A, and everybody else prefers A to B. So this is an example of a semi-decisiveness profile. Everybody in the group prefers B to A, everybody else A to B, and we do know that the collective preference relation is B is preferred to A. So that means whenever this group prefers B to A and everybody else has the opposite ranking of those two alternatives, the collective relation should be B is preferred to A. And that is what semi-decisiveness means here. And if this group is semi-decisive over some pair, we are again using this insight here, then the same group is decisive over all pairs. Okay? And this is probably also what you would have expected. So in the first case, this is a decisive group. In the second case, this is a decisive group. Okay? And both of these are non-empty. That means as we mentioned in the beginning of when I talked about this slide, so we start with the group of all voters, then we partition it in any way that we want. We look at this particular preference profile and we get as a result that either the first or the second group is also decisive. Okay, then we have found a smaller one. And this is basically like a hidden induction now. We can make this smaller and smaller, and in the end we have a singleton decisive group, and that would be a dictator. Okay. And that completes really the full proof of Arrow's theorem. So I didn't omit anything. So all of this is on these two slides. Right, so 2 points that I did mention already. So for this step, quasi-transitivity does not suffice because this transitivity application really needs real transitivity. And it exploits that there's a finite number of voters, right? Because if there would be an infinite number of voters, you could keep on splitting these sets into smaller and smaller sets, but that process would never end. So therefore here we really need a finite number of voters. Okay, so as I said, so probably maybe for some of these steps you need some more time on looking at them, but at least so I think you got some insight now, and now you have seen a proof of one of the most significant intellectual contributions of the 20th century. So I hope that is at least somewhat satisfying to you. So just as a reminder what we did prove, so we proved that every social welfare function that is defined on at least 3 alternatives that satisfies PO and IIA has to be a dictatorship. Okay, rather strong consequence. All right. Questions about the second half of the proof? Okay, so if not, let me show you how we can fiddle around with the properties that are being used in the proof. In particular, how we can change the condition of non-dictatorship and then again get negative statements. So as I mentioned before the break, we are not going to prove any of these other statements, but many statements like these have been shown. And basically summarizing like decades of social choice theory where negative statements were shown, which for some years brought social choice a rather negative reputation because some people thought it's like the science of the impossible. So people are just showing what cannot be done rather than what can be done. So if you think about dictatorships, so they are like an extreme example of a high concentration of power in one particular group, namely in a singleton. Here, a singleton has very much power. So we can change this definition and maybe make it not as extreme by saying that maybe some group of voters has too much power, or maybe that a singleton doesn't have dictatorial power, but only what we are going to define as weakly dictatorial power. So these will lead to different variants of the non-dictatorship condition. So as you recall, so when we moved from the Condorcet impossibility to Arrow's impossibility, so we already had like 3 different variants of rationalizability. So this acyclicity, quasi-transitivity, transitivity, and now we are defining different notions of non-dictatorship. So a dictator is just a voter I, such that when this person prefers X to Y strictly, then in the collective preference relation, X is also preferred to Y. That's the definition for social welfare functions. The one in gray here on the slide is the version for social choice functions. Okay, what a dictator can do is he can force an alternative in the choice set and the other one out. Okay. Now a weak dictator is a voter that whenever this person strictly prefers X to Y, then in the collective preference relation, X is weakly preferred to Y. Okay, so that's just, as itself, it's just a reasonable definition. So whenever somebody has a strict preference relation over X and Y, we don't have the consequence that X has to be strictly preferred to Y. It's also possible that we have indifference between X and Y. But what is ruled out by this definition is that Y is collectively preferred to X. Okay, that's why it's a weaker notion of a dictator. And if you think about it in terms of social choice functions, you get this gray definition here, where the intuition is just that rather than completely fixing the choice set, a weak dictator can only push an alternative in the choice set. Okay? So a weak dictator can make sure that X is being selected, but he cannot rule out that Y is selected as well. But what he does rule out is that Y is only selected. Okay, so there are two possible consequences for weak dictators. X is selected and X and Y is selected. It's only ruled out that Y is selected only. Okay, so weak dictator is weaker than a dictator, and that means that because we are usually interested in not having dictators, that if we take the condition that we want to have, like non-dictatorship or non-weak dictatorship, this ordering is reversed. Right? So not having a weak dictator is stronger than not having a dictator. So there are 2 other variants of this that I'm going to introduce. They have nice fancy names that have been proposed in the early social choice literature. There's also this notion of an oligarchy, which is defined as follows. So it's a decisive group of weak dictators. Okay, so that's the complete definition. So it's a group G of voters, which is decisive, which by itself is not necessarily a bad thing. So like majorities, for instance, if you have majority rule for 2 alternatives, the majorities are decisive. But here, everybody in this group also happens to be a weak dictator. Okay, so that is also like a high concentration of power in this particular group. And then finally, we have this notion of a collegium, which is something that probably is most difficult to understand. And what a collegium is a non-empty intersection, or the non-empty intersection, it's exactly one set, of all decisive groups. Okay, so maybe let's again here recall how we had these decisive sets if we had 3 different voters. So these things are, so these little dots here are voters, and we want to draw the decisive sets of voters. And if we had majority rule, for instance, for two alternatives and these three voters, then this would be a decisive set, this would be a decisive set, this would be a decisive set, and then everything was also a decisive set. But here you can see that there are many decisive sets, but the intersection of all of these decisive sets is empty. Okay, so this is just basic set theory. So all these, well, not even theory, it's just an example. So the intersection of all these three sets is the empty set. So there's nobody who's contained in all decisive sets. And if there's a collegium, there are voters who are contained in all decisive sets. So it's something undesirable. So it's not as bad as a dictatorship or as a weak dictator, but it is bad. So we don't want to have a voter who's contained in all decisive sets, because that means without this voter, certain decisions can just not be made. Okay, so now what one can show is that these notions form a hierarchy. So like two of these implications are really just straightforward. So dictatorships are stronger than oligarchies are stronger than weak dictatorships, and then weak dictatorships are stronger than a collegium. So let's look at the first one. So if there's a dictator, there's also an oligarchy. Okay, that's straightforward because, well, an oligarchy is a decisive group of weak dictators. So if there's a dictator, there's a singleton decisive group who is a dictator and also a weak dictator. So clearly we have this implication from dictator to oligarchy. Oligarchy to weak dictator, by definition, an oligarchy is a decisive group of weak dictators. So in particular, everybody in this group is a weak dictator. So yes, there is a weak dictator if there is an oligarchy. Okay, and the tricky thing is only from weak dictators to collegium. So for this, you need that a weak dictator has to be contained in all decisive sets, if there is a decisive set. Okay, so once you have understood this, that a weak dictator has to be contained in all decisive sets whenever there is one, then you can show this implication here. And why is this the case? Well, let's just assume there is a weak dictator, so that's this guy here, who is a weak dictator, so he can make sure that we have a weak preference, or that some alternative is enforced into the choice set. And then there's a decisive set in which this voter is not contained. Okay, then just by setting the preferences appropriately, it's really just like saying there are two different dictators. This gives a contradiction because, well, this decisive set can make sure that A is strictly preferred to B, and this weak dictator can make sure that A is not strictly preferred to B, because V is weakly preferred to A. Okay, so whenever there is a decisive set, then it has to contain a weak dictator. Or if there's a weak dictator and there's a decisive set, so then this weak dictator has to be contained in the decisive set. So that almost proves this implication here, but I say almost because it's not clear whether a decisive set has to exist in the first place. So there are some functions where there is no decisive set at all, and then you can have a weak dictator, but no collegium, because there are no decisive sets at all. And that's why we here assume Pareto. So if you assume Pareto optimality on top, well, then the set of all voters is decisive, then you definitely have a decisive set, and whenever there is a decisive set, then this implication here holds. Okay, I somehow sneaked in another proof, even though I promised there wouldn't be more proofs, but yeah, at least that gives us the complete picture of these four properties here. Okay, and that shows how we are going to look at these different variants of the Arrow's impossibility, because rather than making this non-dictatorship assumption, we can make the stronger non-oligarchy assumption, or the even stronger non-weak dictatorship assumption. So we can make one assumption stronger and at the same time maybe make another assumption weaker. Okay, so let's see what I have in mind here. So this is a slide that I put very much effort in many years ago. So because I read this literature about Arrovian impossibility results, so there's even a book from, I think, the 70s, so there are probably even many more results by now, which is just called Arrow impossibility theorems. So it's a plural. So there are many theorems that are similar to Arrow's theorem, where people have like fiddled around with these properties and still got negative results. And basically what I'm doing here is, if you start counting with Condorcet, that would be like 200 years ago. I'm summarizing 200 years of negative results in social choice, and that will be like almost everything that we have to say about negative results in this course. From then on, we will talk about positive results. But these results define the boundary of what can be can be achieved in social choice. So we have these 4 different categories of properties. Okay, so this is there should be no dictator, there should be no oligarchy, there should be no weak dictator, no collegium. So this is like the turned around hierarchy that we had from the previous slide. Neutrality, as we defined it, is stronger than IIA, so that we mentioned last week. This here means no condition at all. So we can weaken IIA in one case to the empty condition. Positive responsiveness is stronger than monotonicity, and this is stronger than Pareto optimality. So this is something you proved, I think, which requires this ugly star assumption, which you had on the last exercise sheet. And then we have these 3 different types of rationalizability. Okay, so now we are going back to social choice functions, where we have these 3 different types of rationalizability. You can also think of these for social welfare functions, where the collective relation doesn't need to be transitive, but maybe only quasi-transitive or maybe only acyclic. It's equivalent. And also this is equivalent. So this is really summarizing lots of, basically everything you know so far about social choice theory, except the 2 alternative statements. Rationalizability, we showed in the second lecture, is equivalent to alpha and gamma. And then there was another proof or theorem by Arrow, where he showed that alpha and beta plus is equivalent to this condition here. And conditions become weaker if you go from top to bottom. Okay, so first statement that we looked at was this Condorcet-May impossibility, which uses neutrality, positive responsiveness, and rationalizability. It also uses anonymity. Unfortunately, anonymity doesn't really fit nicely in this hierarchy here. So anonymity is stronger than non-dictatorship that we have established last week, but otherwise it's incomparable to those 3 conditions here. So that's why I didn't. So I could have drawn anonymity here, and then it would have implied non-dictatorship, but it's incomparable to those 3 here. But these are the conditions for the Condorcet-May impossibility. And now we move on to the Arrow impossibility theorem, where the idea is to get rid of anonymity and make it much weaker to non-dictatorship, weaken neutrality to IIA, and also weaken positive responsiveness significantly to only Pareto optimality. Okay, and this is what we get here. We have very weak conditions here, and at the same time we have strengthened rationalizability to transitive rationalizability. Okay, so this is what I think the figure that I showed you last time and also at the beginning of today's lecture. 3 conditions become weaker, 1 becomes probably only slightly stronger. That's the Arrow theorem. Okay, and now what people have been doing is that, for instance, this is, for instance, a theorem that has been reproved by many people at the same time, so they independently found the same statement because there was this open question of what happens if you only have quasi-transitive rationalizability. If that's the case, then we also get a negative result. We don't necessarily get a dictator. So Arrow's theorem is really very efficient that you need exactly those conditions. Once we move one condition stronger, you need to make something else stronger in order to still get an impossibility. But if we move down here, then we have to move up here, and then it can be shown that there is an oligarchy. So this is sometimes also called the oligarchy theorem because it was proved by Gibbard, but also by a couple of other authors as well. And I think that's the T exercise for the upcoming sheet. Yeah, you don't need to be able to prove it by yourself, but it's like a similar proof than the one for the Arrow theorem. Okay, so then I think quasi-transitive rationalizability to me is always like a strange intermediate notion. So rationalizability is usually my favorite one of these because it's necessary and sufficient for always making choices. So this is something we proved in the second lecture on choice theory. So that acyclicity is exactly this notion of a preference relation that is necessary and sufficient for maximal elements to always exist. So therefore we can go down to rationalizability as well. And then it turns out, well, if we make this condition stronger here, we still have a negative result, the Mas-Cole Sonnenschein impossibility. So there's still an oligarchy if we strengthen Pareto optimality to positive responsiveness too. As you can imagine, so there's also another version for rationalizability now. If we think positive responsiveness 2 is too demanding, so I usually think positive responsiveness is really quite a strong condition because ties have to be broken immediately. So there's some notion of decisiveness inherent in this definition. So if you think what happens if we only have monotonicity, okay, well then we get another impossibility which uses neutrality, and then in the consequence we only have a weak dictator. No oligarchy anymore, but there's a weak dictator, which is also bad. I think there's 2 more. I think this can be weakened further to Pareto optimality, I guess, right? This one seems pretty cool. I'll tell you about one of the caveats of this theorem in a minute. So it only uses Pareto optimality, only rationalizability. It doesn't even use IRA, which seems really puzzling. So there's no condition of this kind here. But then the consequence is also, out of these here, it's the weakest ones, because there only has to be a collegium. Okay, so I gave you an example before where I said that collegiums shouldn't exist. But yeah, I'm going to say in a minute why this statement is maybe not as strong as it seems. And I think there was one more. Where, okay, so if you don't like the notion of a collegium, you can have the consequence of a weak dictator, but then you need to go all the way up here. So you also assume neutrality. And this is surely not exhaustive. So I just picked my favorite theorems and then I put them into this animation. I'm pretty sure there are other variants of Arrow's theorem, which probably even use further properties that are not on this slide. But I don't want to bore you anymore with any negative results. So the main point of this animation here is that people have looked at ways around Arrow's impossibility, but like most of the standard ones, like just requiring the collective preferences to be only quasi-transitive or only free of cycles, so that's just not enough. And also, there's even a version of the theorem where you don't even need IIA. Now, I said there are some caveats regarding some of these theorems, and this is what I just dropped down here. So some of these theorems require extra assumptions on the number of voters and alternatives. So one thing that you may recall from last time, so this Condorcet-May thing required at least 3 voters, otherwise it doesn't work. So you need this Condorcet paradox profile, which requires 3 voters. It doesn't work with 2 voters. So which Arrow doesn't. So Arrow's theorem only needs 2 voters. But these are really just like really minor differences. Who cares whether it's 2 or 3 voters? It's an impossibility. But here it really becomes quite drastic, because these 3 theorems require that the number of alternatives is at least as large as the number of voters for the impossibility. And that's like for some applications that is given, but for most applications, if you think about voting, for instance, you usually have many voters and few alternatives rather than the other way around. And this one here, it's even strict. So the number of alternatives has to be strictly larger than the number of voters. And if these conditions are not satisfied, you can come up with rules. For instance, I think Borders rule, for instance, then would satisfy all the conditions in the theorem. So it's you can, yeah. So this is really like, it's only in gray here, but these are important restrictions on these theorems. Okay, but okay. One other thing I wanted to show here is that you can now ask the question of how do we continue? So because like today's lecture really sets the course for the entire semester. So we have all these negative results. How do we continue now? And one of the possible escape routes that we will consider is looking at rationalizability. Okay, so because most of these conditions, so of course we don't want functions that are dictatorial or that even only have an oligarchy. IIA we also take as given, Pareto optimality is given, but maybe how about these assumptions here? So it seems like Arrow showed that it's too strong to demand that there is something like a collective preference relation of the entire society. So this just doesn't exist under reasonable assumptions. So it's too demanding to think that we can treat a society of agents as one rational being. It's really almost like a philosophical statement, which I said earlier. So it's if there are at least 2 voters and 3 alternatives, this society doesn't satisfy basic rationality assumptions that we usually make of individuals. So we try to use these kinds of conditions here. So, but if you only look at this column here, we have seen that there are impossibilities that only require rationalizability. But we have seen these equivalences here in terms of consistency, right? And that's why we talked so much about choice theory in the second lecture, because we are getting back to these conditions at some point in this course, and only take one of these. So one of the possible escapes from Arrow will be one where we, rather than requiring alpha and beta plus, so the conjunction of these is equivalent to this. This is what we have shown in the second lecture. Rather than requiring both of these, we will only require beta plus and not alpha. Okay, so there was also one exercise where something like this was done, and later on we will also look at functions that only require gamma and not alpha. Okay, this is one possible escape route from Arrow's impossibility. So I'm going to sketch in the remaining time a couple of other ones, just very briefly. So what the theorems have shown, that rationalizability or consistency, which are equivalent to each other, are incompatible with collective decision making whenever we have at least 3 alternatives. So we will have, I don't even know, I think 4 escape routes in this course. Yes, 4. The first one is an implicit assumption in all of these impossibilities, is that all preference relations on behalf of the voters are possible. Okay, I think that's something we also briefly talked about last week when we looked at this Condorcet paradox. So maybe we can look at sets of preference profiles which rule out the Condorcet paradox. Maybe we can declare, well, the Condorcet paradox is just something weird that usually doesn't happen, and let's only look at preference profiles which are different than those. So we can look at classes of preference profiles for which it turns out, for instance, that the majority relation cannot result in cycles, and then we get positive results. That's what we are going to do starting next week. I think it's really just the lecture next week. And then we will get very positive results in the form of 2 functions, one called approval voting and the other one is called median voting. Then another escape will be to just replace consistency, this alpha, beta plus gamma type conditions, and use similar conditions on the sets of voters, which I think I maybe briefly mentioned in the first lecture. So these conditions will be of the type, we have one electorate and we apply a social choice function, and then, for instance, alternative A wins there, and then we have another electorate and alternative A also wins there, and then if you take the union of these 2 electorates, then A should also win. So it's like, it seems like gamma, but it's really for different sets of voters rather than different sets of alternatives. And this condition is very fruitful because it can be used to characterize scoring rules, like borders rule, plurality, and then later on we will also characterize a rule which is computationally very interesting, which is called Kameni's rule. Then the third escape route is really what I mentioned on the previous slide. We ignore contraction consistency, alpha, because this is really the essence of what is used in the impossibilities. So at one point we will realize that all these impossibilities still, or almost all of these, still hold if we only require alpha, which is weaker than transitive rationalizability and weaker than rationalizability. And we only take expansion consistency, and this will be the bulk of the course, because there we will characterize many social choice functions that are just based on the pairwise majority relation. So they are called pop cycle, uncovered set, bank set, tournament, equilibrium set. So these are all functions that are based on the pairwise majority relation that satisfy expansion consistency conditions. And finally, so in terms of these escape routes, we will actually weaken both consistency conditions. So that's, I think, at this time a bit difficult to explain how we are doing this, but this will lead to one specific social choice function, which is called the bipartisan set, which is connected to game theory because it also uses the notion of Nash equilibrium. So this is not the curriculum for the rest of the course, because once we are done with that, we will also talk about strategic manipulation and this participation property that we introduced in the beginning. But for the next, I don't know, at least 4 or 5 lectures, or maybe 6, this will be what we are doing. Trying to evade Arrow's impossibility. Okay, so I promised I might finish a bit earlier. So now it's only 5 minutes, but I wanted to show you this outline, because then next week we can directly start with the first escape route from Arrow's impossibility. Okay, thanks for your attention.